Welcome back. This is lecture 31. So in the previous lecture we were talking about matching networks, right? And we saw that under the assumption that under the condition that there is the matching network is also lossy, right? And under weakly lossy assumption, that is the loss in the matching network is significantly lower than the loss associated with the power delivered. Note that power delivered is also a loss with respect to the overall network, right? It is not a stored power. So if that is the case, then we saw that power delivered is equal to E in by 1 plus Qn over Qc, right? Where Qc is the Q factor of component and Qn is Q factor of network taking the load resistor into account, right? So if the components were ideal, right, if the components, for example, the inductor is lossless, capacitor is lossless, and so on, then Qc is infinite, then power delivered will be equal to power that enters the matching network, right? But under the condition that there is a finite quality factor for each component, which is a realistic scenario, you are never going to get an inductor with no loss, right? We saw examples of how loss creeps in when you do a layout of an inductor. So which means that you are stuck with some quality factor of the inductor. Now as a designer, we will have to then design circuits that, given a quality factor, a finite quality factor for an inductor, is there a way of reducing the loss? Clearly it looks like if Qc is finite, right, if Qc is fixed, and you design something with a very high network Q for whatever reason, then you clearly see that the power delivered will be a fraction of the power input, right? So that is not something that we would like to do. So the takeaway from the previous discussion was, for a given Qc, reduce Qn to increase efficiency, right? So efficiency is the amount of power that you are delivering with respect to amount of power you are inputting to the network, right? So any loss is a degradation of the efficiency. Now the problem with this argument was the fact that the Qn was related to the turns ratio of the equivalent transformer, right, or the impedance transformation ratio of the matching network, right? So for example, we had this scenario. So if this impedance is R, this impedance will be Q squared times R, right, or Qn squared times R, isn't it? Where Qn was how much? Was it, by the way, this is approximately, there is actually Qn squared plus 1 times R, so you have to always keep in mind that there is a approximation associated with it, where Qn was essentially omega L over R, right? So if you wanted this, if you wanted to increase this R by a factor of, let's say, 16, then you would naturally want Qn to be 4, right? So that is related to whatever requirement of the turns ratio of the equivalent transformer that you are making. You do not have any choice of deciding Qn once you decide to upconvert R to some higher value, right? So for example, if I say this is R low, the impedance looking here is R high, then I am essentially saying that R high over R low underscore under root this is equal to Qn. So if R low is not clearly not in our control, because that is, if it were in our control, we would have changed R low right away. There was no need to transform it to a different impedance. And if I want to transform it to R high, so then naturally means that I fix Qn. So if Qn is fixed and the inductor is also lossy, if the inductor has a weak amount of loss, and this is R int, then your QC is essentially omega L by R int, which is also fixed, which means you live with whatever efficiency that you can get. You cannot do anything, right? So that might or might not be useful, but at least as a designer, when we are faced with these type of constraints, we have to look for architectures which can help us break this trade-off, right? It looks like the moment you set your Qn, or rather moment you set your R high to R low ratio, you are setting the Qn, and naturally you are setting the loss, right? So we would like to break this trade-off, right? So one way to go about thinking about it is, let's again, I'll go back to that transformer analogy. So if I have a transformer which is like this, so n is to 1, this is R, this is R low, this is R high, which is n squared times R low. This I can also do in 2 steps, right? I need not do it in 1 step. I can do it in 2 steps. Let's say I have one transformer here and I have another transformer here, and I call this n1 is to 1 and I call this n2 is to 1, and here I have R low and here I have R high. And note that now I have an intermediate step to take care. The intermediate step I call this Ri. So this Ri is how much? Ri is n1 squared times R low, correct? So R high will be n2 squared times Ri, which is n1 n2 whole squared times R low, correct? So if this is the case, then looks like there is another way of converting impedance from one to another, right? Like a cascade of matching networks. Now the question that we should ask ourselves is that if we do something like this, is there any way of having a different loss, right? Because it even though now it is a function of n1 and n2, right? But note that now I can maybe change n1 and n2 or size n1 and n2 in such a way that the losses in each of these networks can be slightly different. Now what is the thought process? The thought process goes back to this: why does high Q networks tend to have more loss, right, for a given component Q? Is because if you think about it, when you are choosing to go for a high Q factor, what are you essentially doing? You are saying that I want to have lot of drop across this inductor, correct? You are essentially storing a lot of energy across the inductor. Or you can think of, if I have, instead of inductor, I have a capacitor, you are storing a lot of voltage across the capacitor, hence half CV square will also be quite large, right? So moment you have a lot, you are depending on, so in other words, in order to get to high Q, you are depending on storing a lot of energy in your matching network, and part of the stored energy is kind of delivered to the load, and if that ratio of the stored energy to the load, power delivered to the load energy, is high, then you kind of end up getting a high Q, and hence you get high amount of impedance transformation, right? So the key thing to note is that in order to get high amount of impedance transformation, you have to store a lot of energy in the matching network, correct? So now so naturally, if you have a lot of energy stored in the matching network, and the matching network itself has some lossy element, which means that higher the energy stored, more will be the loss in the matching network. So if we do this, instead of having straight away one-shot impedance transformation, if we do it in multiple stages, then the assumption is, now each of these 2 stages don't need to store very high values of energy, right? The energy storage, amount of energy stored can be distributed among multiple stages. Now, if I distribute the energy stored in multiple stages, which means that each stage will have low amount, I mean, smaller amount of energy that is stored, which means each stage can have lower amount of loss. Now, the question that we need to answer is, if I add up all these losses, is it any different from the single state solution? Is it, if it's different, is it higher or is it lower, right? So that's what we're going to do next. Okay, so let's do that quickly. Analysis is actually quite straightforward, but you have to pay attention to the assumptions. So let's say now what are we doing? We are essentially saying that we have a load resistance R low, and we have a matching network here. I call this matching network 1, and I have another matching network here. I call this matching network 2, and I am transforming this to a different R high. And here I have looking in impedance is Ri. What is the looking in impedance here? This will also be naturally be Ri. I mean, this is what we saw in our previous. So in this case, we are interested to find out what is the overall Q in terms of Qn1 and Qn2, right? So before we go there, let me just briefly refresh your memory as to how we are defining Q. Or let's say this is some matching network which has a Q factor of Qn, okay, and this is some R, and this is, I'm trying to match it to some R high, and note that there is a source here, right? So the whole purpose is because I have a resistance source which has resistance R high, and I want to match it to Ri, right? So assuming that the matching network is lossless, which we were essentially assuming while trying to figure out the Q factor of the network, right? While finding the Q factor of the network, we are assuming that the entire power, the lossy part of the power, is the one that is dissipated in the load, right? So that's the dominant one. So that's why we are neglecting the power loss in the matching network while we are trying to find out the Q factor of the network. So if the matching network is working properly, which means the impedance looking here is R high, correct? So which means that if the network is matched, which means the power that is going in is also equivalent to the power that is coming out, or this is equal to the power dissipated, right? This is power in, right? This is approximately equal to, I should not say equal to, right? So which is, hence we are saying that Qn is equal to omega times energy stored divided by power that is delivered or dissipated. In this case, I am saying power dissipated is equal to power in equal to power delivered. Right? So this is essentially what we have been doing till now, and I will extend this concept for this cascaded matching network case also, right? Okay, so let's do that. So if you have this R high, and this is Mn2, this is Mn1, and if you have R low, I know that looking in here is R intermediate, looking here is R intermediate. Now the power that is getting delivered, that is power in, is approximately equal to the power in that is coming here, right? So this is power dissipated, or power, whichever topology or terminology you would like to use. This is power in for the matching network 1, and this is power dissipated for the network 2, correct? And power under the assumption that the losses in the matching network is not significant, that is much lower than the power that is getting delivered, then I can say that this power dissipated 1 is equal to P in equal to power dissipated 2, right? So if losses in Mn1 and Mn2 are much less than P in or P delivered, which is anyways the goal, right? So then I can say, therefore, P dissipated 1 is equal to P dissipated 2, correct? Okay. So why are we doing all this? We are doing all this because now if you think about the overall Q of the matching network, right, from input to output, what is it? It is basically omega times energy stored in the total network divided by the power that is getting dissipated, right? And now this is power dissipated is the same as power delivered to the load, mind you, because we are talking about a network Q. So this is approximately equal to omega times energy stored by power delivered, right? So omega times energy stored is omega times energy stored in 1 by power dis plus omega times energy stored in 2, the matching network 2, times power dis. Now what are these? What are these? Now with respect to each matching network, with respect to let's say Mn2, what is Qn2? Qn2 is omega times energy stored in the matching network 2 divided by power dissipated, right? But power dissipated not in the matching network, but essentially the power delivered, right? So this is power dissipated 1, power dissipated 1, because we are talking about the network Q. Okay. So what is the moot point here? The moot point here is that Qn becomes network Q becomes Qn1 plus Qn2, and why did we do all this? Ultimately we are after the turns ratio, right? What is n squared? N squared becomes Qn1 squared times Qn2 squared, right? Let's just check whether that is correct. So why did I say n squared should be equal to Qn1 square times Qn2 square? Because what is here, what is Qn1 in terms of our ratios of resistances? So ultimately your ratios Qn squared is essentially Ri by R low, right? This is for matching network 1, and for matching network 2, your Qn square is R high by Ri, correct? So since that is the case, I can say that your R high over R low is basically R high over Ri times Ri over R low, which is equal to Qn2 squared times Qn1 squared. This is the overall turns ratio, right? Or n squared. So this is n squared. So in other words, your n is equal to Qn1 times Qn2. So note that now the turns ratio, even though is dependent on Qn1 and Qn2, but your effective Qn of the network is Qn1 plus Qn2, right? So which essentially means that now by careful choice of Qns, you can have a different optima, right, with respect to the losses. Now because this, what we want to do, this we want to maximize, and this we want to minimize, because why do we want to minimize this? Because this determines loss in matching network, not delivered, loss in matching network for finite QC, right? And this obviously want to maximize because we want to have turns ratio, right? So now without going into the math of it, now when you have something which is with a product you want to maximize, and the sum of this same quantity right? So your product of a quantity you want to maximize and the sum you want to minimize. So what is the, you do your regular differentiation stuff, and what do you get? So the optimum is qn1 is equal to qn2, which means that, so this essentially means that your r high by ri is ri over r low, which means your ri becomes under root r high times r low. So this becomes your approximate decision making of ri, because when you decide to go from, let's say if r low is, let's say 10 ohms, and you want to go to let's say 100 ohms, right? So or rather, let's say I'm just take a round number, let's say r low is 10 ohms and you want to go to 40 ohms, right? So so which essentially means that you would like to have a you would like, if you want to do it in one step, right, your q square becomes 4, right, or q becomes 2. But now if you want to do it in 2 steps, right, then if you want to do it in 2 steps, you ensure that the q is, the overall q is qn1 plus qn2, right, and individual q's are also same because these are also functions of q, right? So let's do an example to clear things up. So if this is the case and you want to, let's say, match, let's take a dummy example. Let's say your R low is 10 ohm and you want to match it to some R high, which is, let's say, 1 kilo ohm, right? And if you do it one shot, that is single matching network, then your qn is essentially under root 1000 by 10 approximately, because I'm neglecting that plus 1 term. So this is 10, which means your power, now if I use that same formula, your power delivered is equal to 1 by, power in by 1 plus qn, which is 10 over qc, right? So now if I use a two-step matching network with the framework that we have just developed, let's say two-step, right? So then what are we saying? We are saying that when we were essentially making this statement, we are also making the inherent statement that qn2 is equal to qn1, right? So from here, I mean, if I do it in 2-step, I know that my turns ratio is essentially qn1 times qn2, which is now qn1 squared, which I want it to be what? My turns ratio, I want it to be 10, right? Because this is my turns ratio is under root r high by r low, right? So this is essentially r high by r low, which I want it to be 10, correct? Which naturally means that qn1 equal to qn2 is under root 10, right? Okay, so how does it help? So let's see. So what is now note that both the networks have identical queues, so I can effectively find out the power dissipated in one of the networks, or let's do it in both networks separately because we're doing it the first time. So let's say I have a scenario where I have, and this is the scenario that we are talking about. This is mn1, this is mn2, and this is your R low. So now we are talking about the power in, and I am trying to now figure out what will be the power going out, assuming some power is lost in the matching network, right? So this is power in 1, right? And this is okay. So what is power in 1? Power in 1 is power in times 1 plus the q of the matching network 2 by the component q, which is under root 10 by qc, correct? And what is power delivered finally? So power delivered is power in 1 by 1 plus, again, under root 10 by qc, because this also has a, this qn2 is under root 10 and qn1 is also under root 10, correct? So this times, this is fine. So with respect to P in, what is power delivered? Delivered is P in by 1 plus under root 10 by QC whole squared, right? Which is approximately equal to P in by, I mean, obviously your QC has to be more than under root 10, right? So I'll use the Taylor series approximation by 1 plus 2 under root 10 by QC, which means that this is again another approximation. So under root 10 is approximately what, 3.1, 3.2, rest the 3.3, so this becomes 6.6 by QC, correct? So note that here the denominator is lower than this case, right? So clearly you are seeing that the reduction of the overall Q of the matching network has led to an increased power that is delivered, right? So the moot point is, if you have to do a large amount of transformation of resistances, it is always beneficial to get into multi-step matching. But the problem with that is, naturally you would end up using many components, which means the area becomes a problem, right? So that becomes a design choice as to whether you would like to have that, whether you have that area to be used or not, right? If you have sufficient area to be used and you also want this large transformation of resistances, then it is for a given value of QC, it is always better to get to multi-stage. I showed you for 2-stage, obviously you can extend it to many more stages, right? Fine. So before we stop with this matching network and the losses thing, I would also need to leave you with some definitions, right? So now, I mean, some definitions that which you all should be aware of is this. So we talked about these type of matching networks, right? This is the main matching network. This is the impedance transformation, and you have a resonator here, correct? So this is our whatever, our low, this is our high. Similarly, you had this and you had that extra component here to resonate out the imaginary component, but the key transformation is happening because of this network, right? Impedance transformation is happening because of this network. Similarly, if you wanted to up convert or rather down convert, you had networks like this, right? And this, or something like this, or other. This color. So these type of matching networks are called L type matching network, or L match, simply called L match. This is L match network, because these kind of look like an L, right? And sometimes what happens is you tend to, so one problem with this L match networks is, we had alluded to once, but let me still mention it. So let's say I am making an L match network, which is something like this, right? And this is essentially there to set the resonant frequency and resonate it out, right? Now the problem here sometimes can be the Q is omega L over R, right? So this is Q of the network. Now let's say I want this Q to be something. If I set the Q to be something and I have a certain value of L, which is determined by some constraint of the type of the value of the inductor that I can realize, then naturally you see that if I set Qn to be of some value, right, then or rather, if I have to mention that I want Qn to be of some value at a particular omega naught, then naturally I have to set the L to the corresponding value. Okay. Now, if I am not able to set L to a corresponding value, which otherwise what I essentially mean is that I am not able to set the resonant frequency or the Q independently, then it becomes a problem. Now you might say that let's set Q to be whatever value we want, and then we resonate it out with the capacitance. right? But the problem will still remain because you have to set omega naught, the omega. So typically, what you need, we need to be able to set the qn at omega naught and omega naught independently, right? Okay. So if we want to do that, and one might say that now we have two variables, we have L and we have C. I use L to set the Qn, and I use C to set the omega naught. In principle, there is nothing that is stopping us from doing it, but the issue will be the profile of your match, right? Sometimes you would want to have a narrowband profile. Basically, that if you recall the Q factor of a second order system, right? It's essentially center frequency divided by delta omega, right? So if your C and your L is both tied up in setting the Q and omega, not Q of the of your network, right? And by the way, this is not the Q of the full network. This is the Q with respect to this Q does not take into account the source R, right? This is Q of this matching network only. So if that is the case, then you are not able to set that. So set your parameters independently. So if you want more degrees of freedom, let's say I want one more degree of freedom, then what can be done is not necessarily have this network. We can also do a two-step matching, but not necessarily step up always, right? So let's say at times you will see network which does this. So this is R, this is L, right? And let's say I go to, so this is Ri, but this is high, right? Higher than R, right? So let's say I say this is Ri greater than R, and by doing this, let's say I have overshot R high. I'm taking an example that I might undershoot or I might overshoot, but let's take the example that I have overshot R high. So let's say Ri is higher than R, and also Ri is higher than R high, where this is R high. Correct? So what do you do then? So this constraint can come because of the sizes of the inductors and the capacitors that you can realize. So if that happens, then I have to step it down. Now what can I do? I can basically have another network like this, which is a step down network, right? Because here I see Ri, so I can do this, and I can do this. I connect it here, and this will be R high. Correct? So now, or alternatively I can have if I want to step this is like, what did I do here? Here I did from R I went to a intermediate, which is Ri, which is overshot R high, and we came down to R high. This is what we did, right? This is R to increase and then decrease. Similarly, I can also do the other way around. If the requirement is to step it down, and let's say I have overshot, then I can also do this. Right? So this is R, and this is Ri. Let's say Ri is less than R, right? And I want to then again increase it because maybe I have overshot. Then I can have another matching network here. So this is right. So this is RL. Maybe I should not use R high, R low, because right now we don't know what it is. But let's say it as R low. So then naturally, what I am doing, I'm starting off from a value of R, and I am going down to Ri, correct? And then I'm increasing to R low. So these type of networks you will often see also in the literature, and they are these are all of them have their own usage and they have their own names also. So this type of network, this network is for example called a pi match. This network for example is called a T match because it looks like a T, right? This is a T match, this is a pi match. So similarly you see there will be different type of matches, but all of them have their own requirements. So if you go through the books, reference books, or even literature, you will going to see different type of topologies, but be mindful of the fact that each of them have their own usage. So when you meet with such a topology, when you encounter such a topology, just pause for a moment and ask yourself as to what was the requirement of this particular topology to be used, because at the end of the day I can do everything at one shot, right? But as we saw, if you do it one shot, there was some issue. So having do it in multiple stages has its benefit, and obviously if you want to do it in multiple stages, then you end up having the problems of higher area and so on, right? So before we stop this matching network business, I also wanted to maybe allude to the fact that let's say you have the option of doing a different types of matches. Which one you might want to prefer based on your architecture? So now note that, I mean, just let's concentrate on this single stage step down L match kind of configuration. So let's say I want to, my plan is to reduce the resistance. So I have two options. I have the option of this and I have the option of this. Which one would I like to use? Now, if I do not give you any other information, then you can choose any. But if I tell you that maybe there is a along with this resistance there is a parasitic capacitance associated with the network, because maybe a transistor gate is connected to it or something like that, right? So then probably this will naturally be a better choice, because this part of this capacitance already exists, right? So hence you will see that in many of these RF matching in many RF applications at lower lesser than 10 gigahertz or so, when you are going to see, you will see networks which have one-sided to be a grounded capacitor. If the terminal impedances of a matching network have grounded capacitances, that those type of networks are often preferred, because I mean, if there is any parasitic capacitance associated with the following stage that it is driving, then it can be absorbed. So that's the only other thing that we should keep in mind, right?